Thanks for fixing the whole MSC. Yeah, thanks. All right, welcome back. It's good to see such a high attendance, given that you don't have to be here. So I appreciate it. Hopefully, we have a fun class today. I'm gonna start with going through R. So I'm gonna need you to pull up your laptops, and we're gonna have some hands-on exercises. So I'm gonna walk through the class and help you if you get stuck. But first, I'm going to walk you through the very basics. So don't worry if you haven't seen, if you don't know R at all, we're going to start from scratch, from the very beginning, and build our way into like more complicated material. Okay. I just thanked you, so listen to me now. Okay. So I typically start with a very brief like review of what went on last class to catch you up, and then we start with new material. So just let's quickly remind ourselves, what is reliability? Four components into reliability. What are they? Let's see. Man, something went wrong. Something is wrong with my pad. Let's see. This is it. Oh, I'm sorry. Something is wrong with my smart pad. Smart. What's this stuff? All right, technical difficulties. I don't think I need to write a lot, so I can skip it. We can get through exercises, and then I try to call someone. Or oh, I see. Okay, so let's see. That's it. There we go. All right. Crisis averted. Okay, so reliability. 4 keywords. What are they? Let's start from this quarter of the class, and we go through it. So this quarter of the class, give me one of them. Time. Okay, we have a time component. Perfect. Let's go through this quarter. What do you mean by condition? Operating condition. Operating condition. We need to know what is the operating condition. Okay. Next group, next batch. What is the function? Okay, we want to maintain a function for some amount of time under a certain operating condition. And what is the last keyword, the most important keyword? Probability. What we are doing is probabilistic, right? It's not deterministic. We cannot like model the entire world. We're going to take a statistical probabilistic approach to everything. Okay, so we're going to start going through probability second half of the class. The first half, I want to get you started with R. But before that, I wanted to make a comment on something you saw in your homework, right? We saw MTTF. What does MTTF stand for? What does MTBF stand for? Go for it. Okay, so this is mean time to failure. This is mean time between failure. Okay, let's come back to this quarter of the class. What is the difference between these two? And just shout out. Okay, mean time to failure is the first time around. You have a brand new system. What's the mean time to failure, right? Okay, what is mean time between failures? Let's go one quarter up this part. Mean time between failures. What do we mean by that? Go for it. Exactly. You have a repairable component now, And then every time you repair it, you have another operation, you get another operation time from it, and then you have a mean time between failures. Okay, so when do these two are exactly the same? Or when are these two exactly the same? Anybody from that part of the class? So let me draw the process to get something like concrete. So I'm gonna call state of operation as 1 and failure as 0, right? I start from 1, it's operational for some period of time, right? And it fails. Now it's in a repair mode, right? It fails, its status is 0. Now we are repairing. Okay, so I fix this and then I start operation. And then it fails and then repair. Operation, repair, right? I can draw it with essentially a time series. It's the stochastic process, right? Okay, so when are mean time to failure and mean time between failure the same? If you repair it all the way to the best status, they're technically the same, right? It's as if you start with a brand new component every time. But not all repairs are perfect. We can have concepts like imperfect maintenance or minimal maintenance, right? So again, this goes back to maintainability, but I wanted to mention that not all maintenance are the same. Not all maintenance bring the system back to as good as new or perfect status, right? Sometimes it's imperfect. So then in that case, mean time between failure is not necessarily the same as mean time to failure. Right? Okay, so I just wanted to make that quick distinction, but again, that falls under maintainability. All right, let's just start with our intro to R. Some of you may be familiar with these, some of you may not, but don't worry, we're gonna refresh your memory if you have seen these before. If you haven't, we're gonna go through everything again. So in R, we have 5 basic objects: character, numeric, integer, complex, logical. It should be very, very similar to a lot of other programming languages you've seen. I think everybody sees MATLAB, right? So we have more or less the same kind of object. So there are types of objects as well. You can have a vector object, you can have data frames, you can have lists. Each of these have certain usage, right? In this class, we typically use vectors and we typically use data frames. In vectors, you have one common type. So everything in a vector can be, for instance, of type character. Everything in a vector can be of type integer. You cannot have integer, character, numeric in one vector. Everything needs to be of one type. Data frames are more flexible. You can have different rows, different columns with different types of objects, right? In data frames. We're gonna look at it more in depth. Here's an example of a few assignments. So for instance, we have an object X to which we can assign different values. In the first line, we are assigning character A to X, which means that now X is a character object. You can assign number 3 to X. In that case, X is numeric. You can assign 4L to X. In that case, anybody knows? It is integer. So if you put a capital L next to it, it makes it integer instead of numeric. 2i, that's complex. And then true, false, that's logical. Right? Okay. All right, let's start by, I'm gonna try to do double screen. Let's see if it's too big or if I can manage. In that case, I can show you the R command next to it. Okay, let's see if it works. Okay, let me first show you R. So in R, everybody has installed R, hopefully. Okay, so you have a console, right? But typically you can like type stuff and then you can hit enter and like get the response right away. But it's good to, like, for some commands we want to preserve them. We don't want to go through our console up and down all the way to find some commands, what they run. Maybe I want to run something multiple times. So it's good practice to always start a new file, either by clicking on this button or going from file. And then now you have a space where whatever you type will stay with you. And then you can also have also your console, that things you can try them out without keeping them. So we're going to do that. And then later on, if you have plots, other things, they would appear here. We're going to come back to it. But let's for now shrink that and then make this smaller so that we can do hopefully side to side. Okay. Is this readable? Good enough? Okay, good. Okay. So let's first try a few things. So character, I want to assign to X, let's say intro to reliability. Reliability 483. Okay, 483. It's hard to type with one hand. Okay, so excuse my slow pace. Okay, intro to reliability. So if I hit X, if I do that, now the character in like the character or like the character object intro to reliability is now assigned to X, right? You can see what's in X by typing X and hitting enter. It will show you what is stored in X, right? Or you can just use the command print to explicitly print it. It gives you the same thing. Not a big deal. All right, so you can look at what's inside an object, let's say X, by calling the function str. I think it's short for structure. What is in X? So what is the type of X now? What type of object is X? Integer, logical, like what is the type? Yeah, I'm asking an obvious question. It's a character. When you call str on X, it tells you back it's character, right? And this is what's in it. It gives you a snapshot of what's in it. Okay, let's go to the next slide. All right, so if you want to make a longer object, more than one object, here we have only one object, right? It's called intro to reliability for 43, that's one object. If I want multiple items, right? Making a vector. Remember, we want to make a vector now. You can do it by concatenating a couple of smaller objects. So here I'm going to assign to X. I'm going to use the function concatenate, right? So concatenate, let's say 483, and let's say hello. Okay, if I press X, then it returns back to me what's stored in X, right? Now it has two elements. Make sense? Okay, now I can make another object. Let's say now I'm assigning to X, C, 1, 2, 3, and 10. If I look up X, what does it show? 4 items, 1, 2, 3, 10. Right? There we go. Okay, if I call str on X, what do you expect to see? Exactly 4 numbers. So it gives you what is the type of the object, a brief overview of what's in it. Now we have a vector with 4 elements, 1 through 4, and then these are the highlight. Like this is 1, 2, 3, and 10 are stored in it. As expected, nothing fancy. All right. So here we are essentially using C. We made a long object, right, with 4 elements. There are easier way or quicker way to do it if there is any particular structure into the numbers, for instance, you want to store in that longer object. So if I go use colon, right, 3 through 10. So it will store 3, 4, 5, 6, 7 all the way through 10 for me in my object. Make sense? Okay. You can also use the command sequence to have more control, because when you're using colon, it essentially counts, right? Goes to 3, 4, 5, 6. So you can use the command sequence. And by the way, you don't necessarily need to assign anything. So let's do it without assign. So I'm going to start a sequence. Let's say I first do it this way. 3 through 10 with a step size of 1. Right? This is going to give me the exact same thing. But then I can have a smaller step size. Let's say 0.1. What do you think this will give me? 3, 3.1, 3.2, right? All the way to 10. Exactly. Okay. So if you have paid attention so far, everything you see this in bracket, there's a 1 everywhere. Now look here. Here's a 1 and then a 12. It's because I had only room for 11 of these items in one row, right? So it's a quick reference to which item in the vector is next to this row. Right? This is the 12th object. Let's count. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? The 12th item in the vector as fall to the second line. That's why it starts with 12. So it's a quick way of what is item 69? This one. Right? So it's a quick way of referencing. Not it. Okay. All right. Moving on to the next one. So I'm assigning -3 through 4. So obviously, it's going to give me -3, -2, -1, 0, all the way to 4. Okay. So for those of you maybe who haven't worked with R, because the other ones, no. So what do you think this will give me? X less than 0. This is X, right? -3, -2, -1, 0, 1, 2, 3, 4. If I say X less than 0, what do you think it will give me? What is that? Exactly. So that is something interesting about R. You have a vector stored in X, right? With what? 8 elements, right? 1, 2, 3, 4, 5, right? 8 elements, right? So when you do a logical comparison with something, like it goes to every element in that is stored in X, compare it with that. So it'll go to the first element, compare it with 0. What is -3 less than 0? Yes, so that's true. Next one, is -2 less than 0? Yes, true. Is -1 less than 0? True. Is 0 less than 0? False. Okay, let's check. So true, 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 all of it false. So it does a logical comparison between each one of the elements in your vector and the new value on the right hand side. So that's another interesting thing about like R. So if I want to get, you see how I can press X and it gives me the values. If I want to get the square of all of these values in a vector, what do I do? What do you think? I heard something. What do you think I should do? Let's forget about square. I want every element in the vector to be doubled. What should I do? 2x. It does element-wise operation, right? If I want to square them, I just go extra 2. So it does element-wise. So it's not vector multiplication, right? It's element-wise multiplication or element-wise operation. Okay. All right. Okay. So let's concatenate a few more. So let's say I concatenate 11 and hot. And when I hit X, you see what happened? Can you tell me what do you observe? What was the type of 11? What's the type of 11? Object type. It's integer, it's numeric, right? What about high? Character. What did you say about vectors? Can they contain objects of 2 types? No, 1 type. So it coerces objects to another type, right? So here, between high and 11, 11 gets coerced to a character. So this 11 is not numeric anymore. If I call str on X, it tells me I have a character object, right? And there are 2 elements, high and 11. So for instance, if you want to do any operation on character 11, it's not going to add it to anything. You're not going to be able to treat it as if it's a number. You have to coerce it back into a numeric value to be able to do operations on it. So that's where it becomes important. If you load a data set, for instance, into R, and then you see you cannot do operations in it, maybe the way they are stored, there is something that now the numbers are coerced into character. So you need to take care of it to be able to like do operations on the numbers. Okay. And then there is also another tricky thing. So if, for instance, you have 12 and T for true, what do you think will happen? Actually, I have it there, right? So I will treat true as number 1. So true gets treated as number 1, false gets treated as number 0. But it's not always the case. So next slide, I think we have an example. Okay, so yeah, here. So here I have x 11 through 13. Oops. Okay, and then I can intentionally coerce it to be character. So here I get 11 in quotations, 12 in quotations, 13 in quotation. These are all characters. If I have logical value, if I have 1, 0, 12, minus 2, and I'm coercing them intentionally to be logical, what do you think will happen now? Again, 1 and 0 are easy, right? 1 is true, 0 is false. What about 12 and minus 2? Again, this is the part that it's mostly the choice of the people who wrote this program, right? Because you could treat anything non-zero as a true or anything non-1 as a false. To me, they are equivalent, right? But they treated as logical. They treated it as if only 0 is false, everything else is true. So sometimes you may need to be careful about that. So 0, if you treat it as logical, it's false. Everything else, everything non-zero, is treated as true. Again, this is mostly a programming choice, but now we have to be mindful of it. Make sense? Okay. Am I going fast? Is it good? Good. All right. All right. One more example. Let's say we have hi, we have class, and we have number 5. All right. So I'm coercing them to be numeric. What do you think will happen if I hit X, if I hit enter? Hi, class 5. What will happen if I force R to give me numeric values back? For 5, character 5, what happens to character 5? Becomes number 5. Okay, that's good. But what happens to hi and class? Do I have a number for those? No. They become NAs, not available. Okay, NAs can introduce a lot of problems when you are dealing with data. And there some functions have way of handling it. We're going to look at it today. But you have to be careful about, again, if you're transforming things from one format to another or from one type to another, you have to be careful of all of these changes that happens to your data. Right? Okay. All right, so slicing. So let's see. I have x 3 through 10. Let's say I want to look at the first element. I can use brackets to slice it. If I hit x period, it will be like 3 through 10, right? What if I'm calling x1? It would give me the first element in the vector, right? Okay, so what is x8? All right, so you can get the length of your vector using the command length, which is 8. All right, so what is x9? Yeah, right, exactly, NA. So again, you got to be careful about the boundaries. Okay. All right, so a few other things. So x1, what was x1? 3, right? What is x? 3 through 10. What is x minus 1? Again, this may be a quick way of slicing again. That's particular to R. Typically, most other programming languages freak out if you give minus something inside the brackets, right? When it's slicing. But here, it will give you everything but the first elements. So it will give you 4 through 10, right? So x minus 5 will give me, what would x minus 5 give me if this is x? Exactly. Oops. Everything but 7. Okay? Let's say I want the second element and the third element. If I want to call them at the same time, I have to put them here in a vector. So concatenate 2, 3 says elements 2, 3, and then you go and slice 2 and 3 at the same time. So 4 and 5. And if you put a minus behind it, it will give you everything but 2 and 3. Pretty straightforward. Make sense? Good. Okay. All right. So let's look at this again. So let's go x minus 3 through 4. We said that x less than 0 will give me logical values back. So if I want to slice only the negative numbers, I can put something like this inside my x, and it will only give me back the negative numbers. Why is that? Because it says call x for these 3 first elements, right? The ones for which x was less than 0. So it would only call back the negative numbers. Make sense? Good. Okay. And the difference between assignment and equal sign. Everything I did so far, instead of using the assignment sign, which is this, you can use equal sign. There are only very few instances where this difference between the equal sign and the assignment sign is important. So one is this example. So let's say I'm calling mean of 1 through 3. This what is the mean of 1 through 3? 2. Okay. So if I want to simultaneously or first assign 1 through 3 to an object and then call the mean of that, right? If this is what I'm saying. So let's say I want to assign them to x and then get the mean as well in one line. This will work. This will not. Oh, this work too. So my code is okay. So that has changed. So last time I checked, or in the last version, this didn't work because assignment went in first, and then this gave me an error, object not found. So at least with the new version, apparently they have fixed it. So depending on which version you have, I tried it at home, it didn't work. I haven't installed a new version in a long time. So be careful about that. That's the only thing that I knew of that you should have been careful about. So in that case, you can always, it seems like with newer version, use assignment and equal sign for assigning values to an object. Okay. Right. Okay. So let's go through this example, and then I want you to then do stuff with it. I guess in the mean. So let's try it out first here in class together, and then I'll introduce more commands to you, and then let you play around a little bit with it. So I have this data frame that I want to load. Right? I have it stored on my flash drive. So let's see where it is first. So mine is under this address, E43R. So that's my address. Okay. So I want to call this file from that folder, right? I need to first set my working library, set working directory, like WD. And then it should look like this. I should put it in parentheses and then in quotations. And then you need to use /. So a few things you cannot forget. Parentheses, quotation marks, /. When I copied it, you saw it was /. So you have to make it /. Otherwise, it doesn't work. All right. Now it's pointing, now R is pointing to my working library, where my file is stored. Next, I want to load my file. So from that working library, so call read.csv, read a comma separated file, right? And then this is the name of my file, time under 2 under failure dot csv, right? Read it and put it in this data frame df, right? Okay, now let's look at df. Any question about how I loaded my file? This is it seems like a very basic command, but time and again, I've seen people have had problems with it. So forgetting the quotation marks, forgetting the forward slashes, forgetting to do first set their working library, then load their file. All right, so just be careful. It seems very simple, but you have to be careful about the command. Okay, so this is my library, or sorry, my data frame. Let's look again, see if I can. All right, so this is my data frame. Component ID, machine ID, supplier location, time to failure in units of hours, right? So just four commands and then 19 items. But let's say this is a very large data frame. So I can quickly look at some summary information about it, right? I call SDR. You can call SDR on any object, right? I call SDR. Let's see. So it says 19 observations, 5 variables. What does that mean? 19 observations, 5 variables. What do observations mean in this context? And what does variable mean in this context? Exactly, 5 columns, 19 rows, right? So every row is referred to as an observation or an entry in the data frame, and each column is a variable. Okay, so these are the 5 variables. R uses $sign for indicating that I'm looking at this column or that column or that column. Okay, so here we have 5 columns. 1, 2, 3, 4, 5. 5 variables, right? The first one is component ID. What's the type? Integer. These are some of the values, the top 10 values in there. Then machine ID, integer, top 10 values. Supplier ID, supplier location. This one is a factor. It has 3 levels. Chattanooga is one of them, right? Then you have time to failure. This one is numeric. And these are the list of 10 items in it. Okay. If you want to quickly look at the head of your data frame, it gives you the 5 first row or the first 6 rows. You see how it's wrapped it around because it doesn't fit it in one column. Or like I've shrunk my R and GUI. Okay, so this head gives you the top part, 6 first rows of your data frame. Then you have tail. It gives you a quick view of the last 6. So very quickly you can examine what's in it, how many variables, how many observations, look at a few examples from the top, you have a few examples from the bottom, right? Okay, let's say now we want to dig deeper, look at machine ID. I want to only isolate from my data frame this variable. So as soon as you press $sign, it pops, a box pops up, right? And these are the 5 variables that you have in your data frame. So for instance, I'm calling machine ID. Now it lists the vector of items that are stored under machine ID in that column. How many items are in there? Don't count. How many items are in there? 19, right? Because my data frame was 19 by 5, right? So it's 19. Okay. Okay, so now I want to do, let's say it was longer. I wanted to know how many unique machine IDs I have, right? You can call the command unique, df machine ID, and it says 2 unique machine IDs. And by the way, did you see how I quickly, so let's do it again. So I call df $sign. Oops. It gave me options, right? I typed the first, what did I do? Machine ID. So now machine ID is highlighted. If I press tab, you don't need to type the entire thing. Just pick it and press tab, it fills it up. So you can work a little bit more quickly. Okay. So we can look at unique supplier ID. Let's say we have 3 suppliers, right? Okay, what else? Let's say I want to know how many locations there are, but I want to know how many components come from each location. So I can quickly tabulate that. So first, maybe let's look at DF supplier location. Here, I have 3 levels: Chattanooga, Johnson City, and Knoxville, right? But let's say I want to do a quick count, right? How many are from Knoxville? How many are the suppliers from Knoxville? For how many components the suppliers from Chattanooga? For how many components the suppliers from Johnson City? So I can quickly use the command table, and then from my data frame call supplier location. It will tabulate the whole thing. It'll say that, okay, from Chattanooga, 7 of the 19 components. And then Johnson City, 3 of the components. And the remaining 9 are from Knoxville. Okay? So now let's look at something that we care a lot about in this class, time to failure. So here, we have a list of time to failure, right? This is a vector of size 19, 19 observations, right? We are looking at that variable. Okay. So let's check if the length is actually 19. Time to failure. Yes, it is 19. This is another way of very quickly looking at the dimension of your data frame. 19 by 5. Okay. So let's go back to our time to failure. Let's say I want to look at, you see how I looked at my data set and it gave me a lot of information? Let's say I want to only look at those components that have a very high time to failure, right? I want to know where they're coming from because they are good, right? It takes them a long time to fail. Those are the ideal components. So let's look at it. So you can use the command subset to subset your data frame. So for command subset, you first use the first element in the function subset is the name of your data frame. Here, the name of our data frame is DF. Good. Okay. Then you want to slice your data frame based on some kind of criteria. Here, I said I want the time to failure, which is the name of my variable. This is the name of my variable. I want to only look at my data frame when time to failure is greater than 40. Right? I'm subsetting my data frame when my variable time to failure in hours is greater than 40. There you go. It's telling me this is the 1, it's component 5, machine ID 1, supplier 3, and supplier location Johnson. Let's say I have you see how I have 5 variables listed right now? Let's say I don't care about all 5. I just want to know time to failure. I just want to know who is the supplier. So I can further slice my data frame, right? I can select which columns I want to appear. Here, I only want to show supplier location and time to failure. There you go. So what's the difference between this one and this one? This one is slicing my data frame only for that column or for those rows for which time to failure is greater than 40. Right? This one is doing that, but only shows me these two variables. Does that make sense? So is it clear? Wherever you select, what select does? Okay, do you have any questions? I'm assuming everything is clear, unless you ask me a question. And I will be happy to go back and show you again. Question. Just press up. Yeah, yeah. On the cursor, press up. Yeah, yeah, yeah. Any other questions? Good so far? Okay, good. Okay, this is an alternate way of slicing. So you can use subsets for slicing, or you can use this other alternative way. Let's look at it. Again, you can pick whichever you are more comfortable with. So you can slice your data frame. You see that your data frame has observations and variables, right? Observations come the first. So see, I put a comma, right? So observations come in the first as the first component. Variables come as the second component. So as my first component, I want to slice my rows such that time to failure is greater than 40. So I say that this variable is greater than 40. Now, which columns to show me? What does that empty mean? It means everything. If you don't specify, it will show you everything. There we go. But like in the previous example, we can refine this to only show us particular columns. So let's say supplier location and time to failure hour. There we go. Good. Okay. All right. So let's say I want to draw a histogram of time to failure. I want to get a look of all numbers instead of getting a look in a numeric sense, just a vector. I want to visualize it a little bit. So I've heard of this command histogram. All right, everybody has heard of this command histogram. Let's see. I can use the command question mark. If I am connected to the internet, this will go to the tutorial and just pull the information right here for me. Histograms come from the library graphics, and essentially they have these properties. Okay, let's call histogram, and let's plot df time to failure. Here we go. I have a histogram of the time to failure. I can change the color. I can change the title. Okay, very quickly. Let's go back to his. So these are the items that I have control over, right? X is my input data, right? Then I have control over breaks, control over freq, which is frequencies or not, control over whether it's probability or not, control over whether it's density or not, what is the X limit, what is the X label, what is the Y label, and so on. So I have a lot of control. How come I didn't need to specify all of these? How come I could just say hist, essentially X, right, my input data, and it plotted something for me? What happened? These are the implicit assumptions of histogram command, which we refer to as defaults. Those are the default values. They figured that not everybody wants a lot of control, right? So you can have as much or as little control as you want. The bare minimum is to give me data. I want to plot it for you. I want to plot a histogram. But if you want to change the color, go at it. If you want to change a label, do it. If you want to change the title, right? So you have control, but you don't have to specify all of those things. So let's say, for instance, we want to change the breaks. So I'm going to call the breaks function or a command. Um, or element, I don't know proper word for it. Okay. So I'm saying put my breaks at 0, 10, 20, 30, 40, and 50. Now instead of, let's compare very quickly. This was before, this is after. Depending on which one you find more informative, which one is more relevant to you. Maybe you want to focus your attention on those components whose time to failure is below 10. Maybe that's too quick for you, right? You can quickly count, oh, 4 fall in that break. Whereas with the other one, it's a little bit more difficult to count. You have to count this and count that and add them. Maybe you want to just look at it as a snapshot. So the bottom line is you have control over a lot of things, but you may not necessarily know of them. You can look at like tutorials or like the documentation to see what are the options you have, what kind of controls you have. All right, so now I'm gonna go through a few new commands, and then I'll ask you to actually load the data frame, and then I'll come to you if you have any questions. So first item that we want to look at is mean. All right, everybody familiar with mean? You just sum of the values, divide by the number of the values that you summed up. Right? It's a measure of the center of the data. It's a good metric to kind of summarize your data very quickly to get a look at it, right? And mean time to failure, right? Mean time between failure. Essentially, those are means, but those are means on a distribution. So we're going to talk about that. This mean is just to simply add numbers up and divide by the total number of items that you have added. So it doesn't necessarily need to match any of the numbers you have. It's just an average of them. Okay. So, all right. So why don't you try this? Load the data frame. It's on Canvas. So log into Canvas, download the file, and store it in a folder, and then use the command set working directory, point it to that folder, and then call the command read.csv with the file name, load it, and then first tell me what is the mean time to failure. In the data set, we looked at the whole 19 numbers. We never looked at the mean. Tell me what the mean is, then do this. And then tell me what happens and see if you can figure it out. There are hints here. And I'll start walking, so let me know if you have any questions. So, like, if you have any equivalent to like my like, I want to know like how many folders. Yes, except for all the data to the base. Does it exist? Is your file there? No problem. You don't have to do that. Adam, you need to yes, mark so instead of oh, because you didn't run it. You have to put your cursor on top of that to be able to run. Oh, did you run the whole thing? I just ran. Okay. So we started with okay, but then
I'm on
they,
Linux.
yeah. No, come on, Linux is the best, right? Because you have absolute control. So any Mac user is loaded with this. Okay, so okay, so you use users and your file.
Yeah, I remember the no.
Okay, so let me right. There we go. They could make them with reloaded. Load the whole thing. Because
And then she called.
yeah, call the perfect. Alright, that was it. Thank you. So this is then you have you need to you don't really imagine how people imagine like how to do it because I am not right. That one is not I am not helping you. Really can imagine how to do it. Just stand up and like you can you want to speak if you don't mind.
Okay,
Sorry, I'm
yeah.
putting you on the spot, but
Yeah,
like
you're good.
you're helping me.
Yeah. So if you have a Mac, if you go into your terminal and copy and paste your folder that your stuff is saved under, it'll show you the like routing of that folder, and you can just copy and paste it into this set W. And you have to change all the like backslashes to forward slashes.
So when you say go to your terminal, can you more specific? Give instructions.
Yeah, go like the spotlight search. If you just type in terminal, like pulls up the command line. You just copy and paste like the folder that you saved your CSV file into, and then it'll show you the full address of it. I don't know. My computer got reset a couple weeks ago, so like, the names and everything got on there. No, no. Can you also, if you have Mac users who have figured it out, can they show up hands? I need help. So you're helping me, right? Okay. Anybody else who is interested and can help me walk through the class, help students? Okay, when it starts loading, can you help the Mac users? Oh, Mac users, fix it. Oh, you're Mac user, right? You can load everything and find the where your file is. Can you help us? Sorry about that. Didn't anticipate. Listen, anybody else has problems finding where their file is? Okay. Did you figure it out? Can you help us? Yes. Yes, down there. You have a problem or you have fixed? Okay, so let's who else has figured out how to maybe I can ask them to do me and you know what? Let's see if we can help you all together.
You have HDMI?
Nine. Okay. I'll help you. So control control I. Control I. Okay. You go over your file. Yeah, no, that's not gonna help you. So have you downloaded the file storage number? Can you go to your folder? No, go from your. Oh, you're a Windows user. I can help you. So go to your file. Yeah. And this is where your file is stored. Done. All right. So this is the DC one. Click there. Yeah. Copy that. Forward slash. Mark. Anybody else have problems? Fine. Nice. Anybody else? Yeah. I don't know. What's going on with that? Anybody else have problems? Everybody good? Everybody good? Sorry about that. Anybody else? Anything. Now I'm proficient in Mac, in Windows, and like everything. Bring it on. Any other problem? You good? Got it. Is that where your file is stored? Where did you store your file? Okay. But is it in go to this desktop? Is this where your file is? Alright. So click there. Hmm. Can you search somewhere else because I don't know where that is? Copy to a folder. Go back to this. Maybe maybe documents. Maybe like yeah. That is it. Okay. That one. Now click there. See that surface. Bring it, and just yeah forward slash. All right. What did you get? Yours on. Fix it. Okay. New Windows. Okay. Is that where your file is stored? Can you show it to me from this sheet here? Okay. You are. So click there. That's okay. Yeah. Okay. Documents 43. Not one? No. This is new. Hmm. You want to run again? No, I don't. I don't think you should change that. It works. It's like maybe when you pop it, it like it changed something did it. Maybe it did. Yeah, or something weird. Okay, I'm glad it's everybody loaded their files. Step one, everybody loaded their files. Good. Okay. So I give you a couple more minutes to tell me what is this mean time space. Don't worry about the second bullet. Let's see if we can find time to failure. Good. That is a success. All right. What is time to failure? 22. Good. All right. 22. Let's check. Let's see. So I bet this is what you did. I bet this is what you did. Okay. DF time to failure, right? And 22.22. Perfect. Okay. So do this then. DF. Let's do it. So have your file here because you're going to come back to your file. Let's temporarily change something. So do it in the console because we want to, after making this modification, figuring out what the mean is, then we want to come back to the original file. So let's not mess up this thing this precious thing we all worked so hard to get, to be able to load all files, right? So just do the change in the console. So call df row number 12 or observation number 12. I want to set that to NA throughout. So let's check out what happened. Yes. Look, we messed up row number 12. It's human error. Okay. So now I want to look at mean time to failure. Right? This is my DF, mean time to failure. Oh, well, it doesn't work anymore because there is an NA. Okay, what should we do? You have a hint. Check out mean. Check out the function. Call mean in your console. It will retrieve the tutorial. See if you can find anything in there that will help you deal with NAs. Look it up. If you call that alone, it doesn't know what you're talking about. Let me classify to the figure object. You're oh, so like you say that. You know, oh, you know what? Because you have an extra here. Don't say that's not directly. Remove the last part. If you find the area CSV, that's what it is. You want to just 22 and 32. you need a position, social position, not it's not. You're gonna reload it. But for now, let's figure out how to I didn't do that. Yeah, for now. But still, you want to because that's the way of it. I kind of thought I would do that. Alright, what's the question? Okay. First question. I wish you had downloaded our did you do the step did you uh, this is on. If you first type your ID, you can download that. Make it up. Yeah, that's it. Open that. That's like that. Yeah, this we almost got out, but let's figure your quality. Can you show me the folder? Okay. So click here. Number one. That is definition one, right? And then forward. Did you know your data frame? I don't think your data frame is loaded. There's something off there. So, nice. You have the so let's try this group. I want to put on the first line. No, that's on the line. So that's why I want to highlight. Highlight the row that we can now go by. No, I think that's on the last. That one line. Let's find the second one. That one line. So it's not like there. Highlight only there. Yeah, just that. And okay, that's there. And that's short. Oh, you know what? You type the whole thing. You run it as that, and you run the last one. You have to run it from the top. Yes, but if you want to only like run it one command or something, then highlight whatever you want to run. It was good. Oh, forget, put it back to oh, God. It is. Oh, well. I'm recording, so hopefully. Let me call one of my teachers. Thanks. Yeah, I got it. Hey, hey, how's it going? Hello, can you hear me?
So the camera is not recording. Can you call one of the other TAs if you're not on campus to come check it out? Just come to class. I don't know. Camera is not working. It's like the shutter is closed. So you need to send another TA. Alright. Everybody got it? What number did you guys get? 23. Alright, let's check. Okay, so if we check mean, the command mean, see what we find. All right, you see if you scroll down, there is this command, right? And then when we read it, it says a logical value indicating whether NA values should be stripped before the computation proceeds, right? So if you turn it on, it will remove all NAs and will do the job. So let's check. NA.rm equal to T. True. There we go. Now we got an answer. It was interesting. Somebody did something I hadn't thought of. So you see how we know that number 12 is a problematic one. So they said, oh, just use the entire row except for number 12, right? Minus 12. And then now we remove the NA, and then we got the mean. But then you need to know where it is located. Whereas with this, you don't really need to know anything about where they are. But I thought that was smart. So actually, this class has another perk. If you do something I don't know, or if you teach me something new, or you answer one of my questions well, you get a chocolate. Hopefully you're not allergic to peanuts. But there you go. Of course. I have one more chocolate for the rest of the night, so make it count. All right. Do you want to take 10 minutes break? And then we come back, we go through the rest of these. All right, let's call it 10 minutes.
So, rookie mistake. I did not know it was posted online. I told you, that's fine. I understood. I knew it was my bad. Yeah, I put my computer at home too. It's gone sitting on my computer. You should have emailed us. You should have told us. I discovered how much money it was. When I was there, I was like, what the hell? And then it was. The thing is, I just turned him down for not turning in, so I want to like don't worry. I mean, I may. This is you have so many opportunities for like I think it's 5 point bonus, but like you're already attending classes, so you're in class attendance. So you can just make it up. Don't worry about it. I'm sorry. I have to like try to keep it straight and keep it fair. need to make like a set. I, it is, or like I try to keep the time self but I want you all to go through the book and then see how it's done. Because again, like they say slightly differently, they explain things slightly differently. So it's like I don't want to say it's like I want to say that's an required book, but like I try to keep the time. Hey, how's it going? It what is it like more? I mean, again, you can you mentioned the first time, right? So you get bonus if you show up for the certificate. That's up to 5%. Yeah. And then the only good thing about attending class is that if you have one, you probably do something that I can see like a very okay, no, that would be fun. That would be enough. But if you prefer, yeah, I don't know, to go home like I don't know what to do the month, it's fine for me. If you prefer to come to class, it's different. Yeah, it's on noon. So you can so first semester stuff or on what okay, ask a question. What is the password? No, nothing needs a password. No, shouldn't. Yeah, just yeah. Let me know if you need anything else. That's it. Mm-hmm. Are you?
All right, let's get back to it. So we looked at mean, right? Mean is just a summary, the average of all values, right? Arithmetic mean. Then we can also have median. What is median? Middle of the data. So if you have an odd number of data points, the middle is right in the middle, right? If you have even numbers, how do you find the median? The average of the middle two. Okay. So in R, we use the command median. So at this point, I'm loading my data set again, getting rid of the row 12, which was messed up. So you can call the command median to find the median time to failure, right? Simple. And then you can also sort your entire data frame using the command order, right? Do you want to try that? Let's take a few seconds if you can figure it out, and I'll type it here. So we want to sort our data frame, let's say, according to time to failure. So this is the unsorted one, right? And then if you call order on whatever you want to sort it based on and call it, then see, it's sorted now based on that. Make sense? All right, let's go next. Then mode. What is mode? Most prevalent, right? So for instance here, what is the mode out of these 10 points, 10 data points? No one? 5. There we go. Okay, so you can use this command, which seems very involved, to find mode. I mean, the reality is we don't typically find mode, so we don't really use mode. Mean and median are the ones that we typically rely on. All right, moving on. Range. What is the range of a data series, or I don't know, a vector? Minimum and maximum, right? So largest and smallest. So you can call the command range. So let's see what's the range of our values for time to failure. So df time Something is off. Time to failure H. So my range is from 3.6 to 40.3. Let's check it out. So DF, time to failure, here. The smallest number is 3.6. The largest number is 40.3. All right, so nothing fast. That thing. Okay, so mean, median, range. None of them tell us anything about the spread of the data around mean, right? Mean just gives me like one average point. Median gives me one average point. Range only gives me smallest and largest. If I want to know more about the dispersion of the numbers, what is the keyword? What is the metric that we use all the time for measuring how spread values are around the center? Standard deviation, variance, exactly. So sample standard deviation or sample variance. So S squared. Who remembers the formula? Let's say we want to start with variance. So forget about square root. What is x? Xi, okay, minus x bar, okay. Square the thing over. How many do I have? How many data points? Let's say n, then over n minus 1, okay. So now what should I do with all of these xi minus x bar squared? X1 minus x bar squared, x2 minus x bar squared. You add them up. Perfect. That was pretty good. You just pulled it out of out of a hat here. Okay, good, good. Anybody? I'm not sure about that. Not quite there yet. All right. Okay, so we had also a shortcut formula, if you remember. There was another formula that started with summation of xi squared minus n nobody x bar squared over n minus 1. And obviously sample standard deviation will be square root of that. Okay, so let's actually calculate that for hours. Let's calculate it. So I'm gonna put this into a new object like x, because x is shorter. So I want the summation of xi squared, right? X squared, right? I want to sum all of those minus n. N is what? The number of items I have, the length. Length of x, n times x bar, which is mean of x squared. Do you agree that this is my numerator? You see, summation of xi squared. We said if we do x to the 2, it will do like pair or like component wise like operation, right? So it will be x 1 squared, x2 squared, x3 squared, x4 squared, right? And I'm summing them. And then minus n is the length, the number of items I have, times average x bar to the 2, okay? So this is my numerator. I want to divide that by length of x minus 1. Okay, this tells me that my variance is 163. Is there another easier way? Sure it is. Let's call the command variance. Same thing. Make sense? So you also have standard deviation of x, which is the same as square root of variance of x. Right? They're all the same thing. Okay, good. Any questions? No? All right. So sample versus population. What is a sample? What is a population? How is sample different from population? Sample comes from population. So population is everything. Sample is a subset of it. You can have certain criteria for this subset. You can have randomly chosen this subset. You may have chosen the first 5 elements to get your sample. Do you think in reliability engineering, we work with samples or do we work with populations? Samples. Why not populations? It's too big. And then at the same time, if you want to test to see when things fail, and if you test it on the entire population, that's kind of the joke is on you, right? Or the joke is on the person who is doing that. So it doesn't work. We have to sample in reliability engineering, right? Because you cannot run every motor to failure to see what is the time to failure, right? So it doesn't make sense. So we work with samples. But then we have a notation for population. Maybe sometimes we want to estimate these values. So the notation we use are mu, sigma squared, and sigma. These are for population level values. For sample, we use x bar and s, right? X bar is for mean, and s is for sample, standard deviation, right? And s squared is for sample variance. Everybody familiar with the notation, right? So they have certain meaning. Okay, and then population variance is slightly different from sample variance, the formula. So population variance is summation of xi squared minus mu n, or n, capital N, because capital N is the size of the population, capital N mu squared over n, right? We don't have minus 1 for adjustment, because that minus 1 is for adjusting, because we are dealing with sample. All right. Okay, so now again, let's do another R exercise. Load the data frame, which you have done already, and then compare the mean time to failure for the items produced on the 2 machines. So you remember we had 2 machines, CF, machine ID, and we looked at unique. 1, 2. So we want to make a decision whether machine 1 and machine 2 are similar in producing items that fail maybe late or early, or like have a particular average time to failure, or maybe they're not different. You want to dig deeper to see what is the reliability of the components built across or made with these 2 machines. How are they different? Let me know if you have questions. You know, okay, let's conceptually talk about it. What do we want to do? We have a data frame, right? In this data frame, we have a bunch of machine IDs, right? There's a 1, there's a 2, there's another 1, there's another 1, there's another 2, right? And each of those have each of those rows, those observations, have a time to failure. So how do we want to look at this data set? Before, machine 1 and 2 were all in the same data set. Now, I want to stratify things, right? I want to make this data set into two sub data sets. One has information about machine 1, the other one has information about machine 2. Then I can easily look at the average time to failure for components built on machine 1 and average time to failure for components built on machine 2, right? Sounds simple enough. Should be able to do it. You should use the command subset to come up with your sub data sets and then look at the time to failure.
So after you set your data set, you want to name the new two data sets. The call one DS1, the other one DS2. The one is DS2. From here, now you want to from here, come. Now, what is the option you want to look at? Yes, okay. Now you have condition on that. Before, sorry, we are looking at content and something else. Now, what is your condition? You want that to be complete. Okay. And then before that, you like, now this is the one, two, and then so you're missing the first and then the second. So you need to say like, this item, what is the item that entitled? The first component is here. It's the first here. Put it in your one. You just need to put it here. And then you have your comma. So before we get started, we say, how to say this here? Now we want to say the two items in cost. So let's no, no. Because now this is pointing to the here. So it knows that it is pointing. So you can use the maybe tell you. Can I help you with anything? But I would probably put it in a music thing so that I can see the actually I think you need double. So make sure you're doing a logical comparison, right? So when you're saying machine ID equals one, you should do it equal. Because it's logical comparison. It's not an assignment. But that means it's so much clearer. Right? Yeah.
All right, so let's look at it. So we are going to do subsets from our data frame, right? And what is the components we are looking at? Machine ID. And then I want to look at machine ID 1. Let's say this is DF1. And then DF2 for machine ID 2. Okay? So now let's look at DF1, time to failure. these numbers, and df2 time to failure, these numbers. Okay, let's look at the mean. Let's look at a few things. Let's look at the mean, for instance, first. The mean of this one is 29. The mean of this one is 14. I can do a lot of things now because I have all the numbers. I can plot box plots. This one, that one. I can plot both. Machine 1, machine 2, right? You see this one is not as spread. So typically in reliability engineering, we want to be sure as much as possible. So we don't like a large spread, right? But at the same time, we prefer the mean to be longer, the time to failure to be longer. So this is from one perspective bad, but from another perspective very good, because this is like, this fails almost 3 times later. Like this one fails on average about 10 hours into the process. This one fails about 30 hours into the process. So that's a whole lot better. But there is something about the operation of this that makes the variability much smaller, right? That is something that we like. So if we had this lower variability on this other one, right, that had a higher mean time to failure, that's the ideal. So we don't get that here. So this is again quick summary of like how we can use visualization, how we can use slicing to be able to look at a lot of things. And this is just extra information on how, for instance, we can add columns to a data frame, or how I can generate a data frame from scratch, because here we essentially loaded a data frame. But you can generate your own, and you can start filling it up. So play around with these two. And then, okay, so one last thing about sampling, so that you can sample with the command sample. You can sample without replacements, and this is a default value. The default is false. If you go with the default, it will just pull. So let's try it. It will pull 8 numbers randomly from the original 19 that we had. Right? Every time I run it, I get new 8 numbers. But I can also sample with replacements, and then I may get repeats here. So let's see. Let's try it a few times to see. Okay, here I got 2 repeats, right? Because, okay, can somebody explain sampling with replacement, sampling without replacement? Just in the name, but I want somebody to articulate it. Exactly. Without replacement, you took it out, you sampled it, you took it out, you set it aside. Now you have fewer, right? You don't have that marble anymore in your urn. But with replacement is you put it back. Okay. All right. So this is all I wanted to say about introduction to R. And this was supposed to take much less of the class time, and I was hoping to get through basic concepts of probability very quickly today. So let's see how much of it we get done today. But then throughout the rest of the class, then we may not see R for like one more session or something, because we are gonna start digging through through probability background, and then we come back introducing different functions about reliability, and then we come back and use R for like plotting things, or estimating parameters, or things of that nature. Okay. Okay, so again, everybody has background in probability. I just want to do a very quick review, a refresher. So this is not supposed to be comprehensive, but again, if you have questions, come see the TAs, come see me, ask questions in class, and so on. Probability, we want to study randomness and uncertainty. We want to quantify this uncertainty, right? For example, what is the probability of selling a certain number of products in a year? What is the probability of a part being good after production or after shipping? What is the reliability of a new component? That is probability. Okay, So when I talk about probability, you should immediately think of a die. Like every probability class starts with that. This whole process is called a random process, right? What are these observations that we can have? What's a name for that? Nobody remembers? We refer to them as random variable is the variable that contains, I can assume different values. So these values that it can assume are called, I'm being picky, I want a keyword, outcomes. So we refer to them as outcomes. What is the set of all outcomes? What is the keyword we use for that? Nobody remembers? Sample space. This whole thing is called a random process. Just want to make sure that you attach meanings to these keywords, and I can easily use them later, and it triggers some particular definition in your head. So I call the whole process random process. The observations you can have are particular outcomes from that process, and the collection of all outcomes, I'm going to refer to it as sample space. This is just our agreement. Okay, so you can have a lot of different collections of outcomes. So for instance, any number greater than 4, odd numbers, even numbers, right? We refer to these as events. You can have a simple event, a compound event, or a null event, right? Can you give me a simple event? You roll a die. What's a simple event? Lands on a 4, right? Observing the 4. What is a compound event? Even numbers. So which is 2 or 6. A null event, it cannot happen, right? And these are my definitions of random process, sample event, outcome, and event. All right, let's go through this very quickly. In the die example, let's say A is observing 1, 3, or 5, and B is observing 4, 5, or 6. What is A union B? Let's go row by row. First, I'm feeling bad for putting you on the spot because you're the sole person on the first row. But let's see. You can pass. Uh, but no. So that is intersection. Okay, I give you that. So intersection is when you have something in both. Okay, next row. Let's go back to the A union B. Okay, so it will be 1, 3, 4, 5, 6. Okay. Next row, A prime. Okay. So somebody came to your rescue. 2, 4, and 6. Everything not in A. But okay, where is everything? What was everything? Yes, everything in the sample space. Right? So that was my sample space. I told you it's a die example. If it was entire integer numbers, right, then you have a different sample space. Okay. A union A prime. Third row, do you want to take your chance? A union A prime. All sample space S, right? A union A prime. Okay. So let's see. Let's say event C denotes observing an even number. What is A intersection C? The row after. Even number is 2, 4, 6. What is intersection of A and C? No. Okay, no. So what do we refer to these two sets then? There's nothing in common between them. They are, you remember the word? Say it a lot. We have a phrase. Go back to when you got priority, a couple years back maybe for some of you, right? These Sets A and C are called disjoint. Disjoint, or there's another word. Or starts with M. Mutually exclusive. Okay, exclusive. Disjoint or mutually exclusive if they have nothing in common. Okay. And again, these are the definitions. So we're going to spend a little bit more time with set algebra. So of course, A intersection B is the same as B intersection A union B is the same as B union A. You have associative laws, A union B, union C is the same as A union B union C. Okay, this one is more interesting. Let's see if anybody remembers. Distributive law. A union B intersection C. Let's go fifth row. That row is very, very popular. So we should find somebody who can help me here. Or maybe sixth row. A union B intersection C. Anybody want to take a stab? No? Okay. And any taker from the row after? Okay, I'm opening the floor. No problem. So it's A union B intersection A union C. Becomes very handy. And here, A intersection B union A intersection C. So you can think of this as this is for instance, a multiplication. This is a plus. Am I right? I think I'm right. Yeah. Okay. Moving on. So Venn diagrams, everybody's favorite when it comes to set theory, right? We have a sample space, we have an event, and this is for instance, we shade it, we say the quantity associated to that, we call it P of A, right? And P of S, the probability of sample space is 1. Right? Okay. But we don't need to talk about probabilities, I guess. Let's forget. Okay. So let's do a little bit of drawing. Let's see if we can draw the Venn diagram for these two. There are two questions. Draw a Venn diagram for both two cases and tell me what you observe. Okay, the first one. Complement of the union of the two events. Where should I shade? You know what complement means, right? It's A prime, right? Complement of the union of A and B. Where should I shade? What was it? Everything but the middle. Is that the union of A and B? Let's mark the union of A and B. Where is the union of A and B? Both circles, everything inside it. So complement of that would be everything outside of the circles, right? So it will be this. Agreed? So, right, this is A union B complement. All right. What about the second one? Intersection of the complement of A and the complement of B. There is that. So complement of A, complement of B, what am I interested in? The intersection, which means that it needs to be covered by both colors. Right? What do you observe? The same. Is that a coincidence? No way. This is called De Morgan's law. You always have that, and it comes very handy. Again, little things that comes from set theory, later it shows up in probability and is very helpful. So you have this and you have the other way around. A intersection B prime, or the complement of A intersection B, is the same as A prime union B prime. Right? And these two are equal to. Okay. All right. So probability you're all familiar with, right? It's kind of like we want to quantify chances or risks. And we typically refer to them as a limiting relative frequency of something happening. So for instance, if you have a coin and you toss it once and you see a head, and you toss it twice for a second time and you see another head, do you say that the coin is broken or unfair, or is it just a coincidence? If you do it for a long time, right, and average out how many heads you see over all trials, then this approach is typically to 0.5, right? So it's in the limit. What is the probability of that, right? But it's not just one trial or two trials, three trials. It's in the limit. So in the limit, if I'm accumulating these and like finding the relative frequency, this kind of converges to 0.5. That's why I say if the fair coin has a 0.5 chance. Okay. So there are multiple axioms, 3 specifically, axioms for probability. We don't have a probability greater than 1 or a negative probability. Everything is between 0 and 1. The summation of all the probability of all simple events in our sample space equals to 1. And then if I have the union of a set of mutually exclusive events, the probability of this union is equal to the probability of the individual events. Okay. So let's go through a few quick exercises again. If two events A and B are mutually exclusive, then what do we know about P of A intersection B? We just said it, it is the null event. If A and B are mutually exclusive, what do I know about P of A union B? Shout it out if you know. In particular cases, yes, but in general, not necessarily, right? When I drew A and B, they weren't covering the entire sample space. So in some cases, you're right. Exactly, that's it. Because they are mutually exclusive, okay? How can I characterize P of A prime in terms of P of A? Perfect. And this is the final, most general equation that we're going to come up with. If two events are not mutually exclusive, what can I say about P of A union B? You remember? It's P of A plus P of B. Exactly, minus P of A and B, minus P of intersection. So this is a very important formula that we learned in probability. Good? Okay. All right, now that it's good, let's look at these 3 examples. You're very quick. You may need to draw a Venn diagram for the last one, particularly, because it helps. Read through it, come up with two events, A and B, characterize what the numbers are, and then go through 1 through 3. And raise your hand if you have any questions.
Everybody knows what 0.5 is, right? So let's say that 0.4 is P of A, 0.3 is P of B. What is 0.5? A union B target A. Good. The formula you're using, haven't chosen it. So we said that yes, A union B is equal to A, but the B minus the A. Right then, and then we have three numbers that goes exactly that. For the question one is the last one. So here we're going to use the so P plus P of B minus so it's taken to the formula is P of A union B is equal to this plus this minus that, but then we have to document so that's here.
So what did you get for the first one? First, what does the question one want? What does it want? Okay, that's the answer. But what does it want? Intersection. So it wants intersection, and you found intersection. Which formula did you use? The sole formula I have introduced so far. Right? So question one. So we had P of A, P of B. We established when we said at least it's P of A union B. And this one wants P of A intersection B. I had introduced a formula to you. P of A union B is equal to P of A plus P of B minus P of A intersection B. There we go. What was P of A from last slide? 0.4. Do you remember the first one? 0.4, 0.3, and 0.5. Okay? We need 4 values in this equation, right? We have 3 of them. What's the fourth one? 0.4 plus 0.3 minus 0.5, exactly 0.2. Okay. So neither of the two will overflow. So think of it in terms of the notation first. What does it want? If it says neither, complement of something. Okay, complement of what? Complement that at least one will overflow. Do you agree that neither means not this nor that? So it's a complement of A union B. Right? So it's 1 minus P of A union B, which is 0.5. Make sense? Do you agree that neither is complement of at least? Right? Then you have it. The last one. I'll give you a couple more minutes to think about the last one. Maybe draw a Venn diagram. We know they have an intersection, right? So there is an intersection. You want exactly one. Okay. Decisions, decisions. Do you have a formula for me? Go for it. Exactly. Or I'm going to summarize that to say that it's probability of A union B minus probability of A intersection B. Yeah, that's the same thing. It's the same thing. It's the same thing. But I had less space. So I'm writing the compact version. So 0.2 minus 0.5 minus 0.2 is 0.3. Right? It's a union. You're taking out the intersection. So again, this problem is not that complicated, but it's still drawing Venn diagrams helped. Right? So try to take advantage of visualization whenever you can. It typically helps me. Hopefully it helps you too. All right, any questions? All right. Okay, so independent events. Everybody have heard of it. When we have two events, the occurrence of one doesn't influence the other one. If and only if two events are independent, we have a formula like that. P of A intersection B is equal to P of A times P of B. Right? But this is only for independence. And independence is different from mutually exclusive. Right? When things were mutually exclusive, their intersection was 0. Right? The probability of the intersection is 0. The two events are mutually exclusive. The set is null. The probability of a null set is 0. Right? When things are independent, the probability of the intersection is multiplication of the two. So they're very different. Don't confuse them. For some reason, people confuse them. They're very different. All right. Okay, so in the tributary example, let's say I'm rewriting the question. So I have tributary A and 2 overflowing with 0.4 and 0.3, right? Now, suppose this is the case. Suppose the occurrence of overflowing in the two tributaries are independent of each other. Now I want to determine that at the probability that at least one will overflow. Again, at least one. In terms of our notation, what is that? If I have A and B. If at least one is happening, this is union, right? If at least one. So I want the probability of A union B. Agreed? That's at least one. Why? Because it either has components from A or B or both, right? So it's at least one of them. Make sense? So okay, so I can write this as P of A plus P of B minus P of A intersection B. I have P of A, this is 0.4. I have P of B, this is 0.3. Do I have this? Multiply them. Why am I multiplying them? They're independent. Independent, so I can write this as P of A times P of B. This will be 0.4 times 0.3. Times 0.3. Right? So again, I switch the keywords, completely different problem, different way of solving. You have to be careful about those keywords. This is this plus this minus that. It's clear, it's coming back to you at waves. It's right, priority is coming back to you. Hopefully brings good memories back. Good. Okay. All right. You guys seem a little bit tired, so let's play a game. Okay. Let's watch this video to set it up. Who has heard of Monty Hall problem? Okay. So don't you can still play. You can still play. This it's fine. But maybe don't shout out the solution. Let's let people figure it out by themselves. Okay. So I could explain the problem, but everything is better with British accents, right? So I'm letting a British speaker explain that. Let's see. Let's increase audio. Oh, no. What happened? Okay. You got the question. All right. Think about it. But I want us to find it in a statistical manner, right? To figure out in a statistical manner. It's a statistic. I'm treating this as a statistics problem, right? So for statistics, we need to sample. I'm using you as examples, like for generating examples. So we are doing this. Pair up two people, like let pair up, right? Pull your laptop up because I want somebody to generate random numbers, right? So we are playing the game twice, two sets, right? One set, you like the person on the left becomes the guest, the person on the right becomes the host. The other set we switch, right? So we have a guest, we have a host. So each one of you is going to play 10 times as a guest and 10 times as a host. Okay. So the host is easier. The host is generating a random number. Don't show the random number obviously to the guest, right? How can you generate a random number between 1 to 3? Sample. Sample from 1 to 3, one number, right? That gives you a random generator because I don't want the game to be biased. So let's check. So this one is easy, right? You just go to R, call sample from 1 through 3, one number. Gives me 1 here, gives me 2, gives me 3, then 2. So this is the door that has the winning prize. This has the car. Again, don't show it to your guest, right? Your guest picks a door, right? You play the game. Then you reveal a door, and then your guest has the chance to switch or stay with their door. Okay, so don't, again, you heard the instructions. You never reveal the door that has a prize behind it, right? You, as the host, you only open the door that has a goat behind it. Is it clear? Okay. So now, if when you are playing guest, I'm not giving you an option because we are doing this again statistically. I want you to either, depending on how you're seated, right? Either choose if you're on the left, pick a strategy 1. If you're on the right, let's say this is left, that door. If you're sitting closer to that door, pick strategy 1 when you're the guest. If you're sitting on this other side, pick a strategy 2 when you're the guest. So I'm not leaving it up to you. We want to calculate. We want to do like an average number. See on average which strategy works better, right? Okay, 2 strategies. Strategy 1, always switch. Strategy 2, never switch, right? And then 10 times out of 10, count how many times you were successful, you won, and how many times you lost. Go to this link and enter the number. So this link will essentially gives the same instructions. So be careful when you're entering. If you were on that side, strategy 1, put it in here. If you were strategy 2, put it in the second question. Don't fill both questions, right? Then we want to compare which strategy was the winning strategy. Is it clear? Good. So pair up. Each pair has to have a laptop because I want the numbers to be generated randomly. And then let's play a game. Who doesn't have a teammate, a pair? You can pair up with somebody from the row before. Okay. So you guys can pair up. You go up, and then if there are 4 of you can pair up.
That's what you want to do. Yeah, want it out. So we compare one. So for now, we get 40. So the host opens the door. So the host picks the door first in their mind. Then you pick a door. Like let's say, okay, so you pick a door. Okay, so you reveal a door. Which door do you reveal? Okay, so you decide. No, you don't decide actually. You you then switch. Okay, so did we win or lose? Okay, so lose. To keep track. Who is winning? Who's winning? Oh, I love it. You have doors and everything. Non-win. Oh wow, that is something's not working. But strategy seems off, right? Yeah. Who's winning?
Right now, I'm losing 2 out of 10.
That's not bad. Why? Think about it. What? Why? Let's put you all 10. Yeah. If you win all 10, you go buy a lorry. You were sitting on the best side, so you were supposed to have strategy. What happened? And you played. You got lucky actually for the policy that or for the strategy that like forced them. Okay, so what what happened? Yeah, yeah. And what one third of the time you get it all the time right. Did you enter it in the right? Everybody played. Everybody got their answers in. So I kind of know what you guys are thinking. That like it was a very unfair strategy to people who were sitting on the left by accident. But okay, so let's actually check what the results were. Again, statistically speaking.
All right, moment of truth. Strategy 1. Oops. 2, 3, 4, 5, 6, 7, 1, a couple nines. Strategy 2, not so much, right? 1 win, 2 wins, 3 wins, and so on. So which strategy is that on average better? Strategy 1, switch, right? I talked to some of you and they articulate very well. So can somebody or does somebody want to speak to the class why strategy 1 so much better on average, or like actually better than strategy 2? What happens with the strategy 1 that makes it so good? Exactly, you increase your chance. So what are we doing? It's essentially conditional probability, right? 1/3 of the time you get it right, first time around, right? If you got it right, there are 2 options for the game, for the host, right? To reveal. And then if you switch, then you get the other one and you're wrong. So by switching 1/3 of the time, you're going to be wrong, right? But think about it. You're going to be 2/3 of the time wrong the first time around when you pick a door, right? Because there is only 1 prize and 2 goats. So 2/3 of the time you're going to be wrong. But then let's imagine that you picked a wrong door, and then the game show host needs to eliminate a door. They don't eliminate the door that is opening to the prize. So they have to eliminate the door that has a goat behind it. And then if you switch, you 100% land on a door that has a prize behind it, right? So essentially, you are increasing your odds of getting the prize by switching, and that's the explanation. Does that make sense? And we all see it statistically again by just tallying the number of times you won. All right, so it's getting kind of late and I'm feeling generous, so you can go. But then next time, I didn't finish what I wanted to. So next time, we're going to start with conditional probabilities, now that we are primed with the game. And we're going to go through the rest of this and hopefully new material. Watch out again for homework being posted tomorrow and quiz posted on Tuesday. Have fun. Have a good weekend.